Good morning, everyone. Today we'll be starting with the two more operations which we have gone through that is shearing and reflection. In the previous classes we have studied, we are in the topic of 2D transformation. In that we have studied what is translation. Second, what is rotation? Third, what is scaling? Fourth, shearing. And fifth is reflection. Okay, so these three we have studied. We have started with the shearing. I've already explained you what is shearing. It is the distortion of the object along a particular axis. Whether I want to distort the object in the x-axis or a y-axis. So shearing is basically has two types. We have already discussed this. If I want to distort any object, if previously the object is there, I want to distort the object along x-axis. This particular thing is called as x-shear, where the particular object changes its shape along x-axis. So if you see the coordinates of particular object, it is a square object and it is being sheared to x-axis. So such type of shear is called as x-shear. Here, if I want to find out what are the coordinates of the final sheared object, what happens here is y will remain as it is. If I want to find out what is y dash will be equal to y. So y dash doesn't changes its coordinates, only the x coordinates changes. Because of that, the shape of the component changes. So x dash will be x plus shearing, how much we are trying to shear it, that is called as a shearing parameter, into y. Okay, so similarly there is one more. If I want to shear it about y-axis, if I want to shear it about y-axis, we call it as y shear. In case of y shear, x components the final x coordinates remains as the original x coordinates, so it remains x dash is equal to x. Okay, so y dash will be y plus shearing parameter into x. We need to remember this thing. So shearing is nothing but change in the shape of the object. So because of that, the coordinates are shifted. We need to identify in which direction the shearing is happening, whether it is along x-axis or whether it is along y-axis. If it is happening along x-axis, y coordinates will remain as it is. There is a change in the x coordinate. In case of y shear, x coordinate remains as it is and there will be a change in y coordinate. So this is the equation we need to remember. So will be much clarified when we try to solve a problem on this. So basically we'll take a simple problem. We'll take the same square, share a square 0, 0, 2, 0, 0, 2 and 2, 2 in along x-axis of 2 units, which is nothing but shx is equal to 2. shx is equal to 2. So if I try to draw the object, so basically we have already done this. So this is x, this is y. Okay, so we'll take this as an origin. So this is 1 unit, this is 2 unit, this is 1 unit, this is 2 unit. So if I plot it, so this is 0, 0, this is 2, 0, 0, 2, this is 2, 0, and this is 2, 2. So this is a square object. This is a square object. I need to share it along the x-axis, that is shx, by 2 units. Okay, by 2 units. So I'll write it as by 2 units. By 2 units. So if you see the formula, there are 2 formulas available, that is called as x share and y share. So as the question is being asked to share it along x-axis, so we'll be using the x share formula, which is, if I take an x share, which is y coordinates remains as it is, x coordinates will be x plus shx into y. Okay, so we'll be applying this formula and we'll see how the change happens with particularly the different coordinates. So first we'll start with the coordinate 0, 0. So what happens? Y dash will be equal to y, which is 0. X dash will be equal to, x is 0 for this, plus 2 into y is 0 for this, so it remains as 0. So the change now is x dash y dash is 0, 0. Now from 0, 0 it has changed to 0, 0, which means that is there is no any change happening. Okay, so similarly if I go with the next point, that is 2, 0, 2, 0. So what will be y dash? Y dash is nothing but 0. What will be x dash? It is x plus shx into y, that is 2 plus 2 into 0. 2 plus 2 into 0. So you will be getting x dash as 2. Okay, so what is the coordinate which we have got? So x dash y dash is nothing but 2, 0. So from 2, 0 it has now changed to 2, 0. That's changed. So there is no change along the baseline. You can see there is no change along the baseline. So we'll be seeing what will happen if I apply for the different other 2 coordinates. Okay, so next one is 0, 2. Okay, so here what happens? Y dash will be 2. There is no change in the y coordinates. X dash will be 0 plus 2 into 2. So because shx is 2 and y coordinate is 2, you'll be getting it as 2, 2 into 2, that is 4. So what is the coordinate you will be getting? X dash y dash is 4, 2. 4, 2. So it has changed from 0, 2 to 4, 2. So this is the shear which is happening. So next we'll go with the final point, that is 2, 2. So if you see that y dash will be equal to 2, x dash will be equal to 2 plus 2 into 2. 2 plus 2 into 2. So what happens here is x dash will be 2 plus 4, this is 6. So what is the coordinates you are getting? X dash, y dash is 6, 2. 6, 2. So what has been the change? 2, 2, 2, it has changed to 6, 2. So these are the different points which you have got after performing the shearing operation along x-axis. So this is the first coordinate. This is the second coordinate. Okay. So we will not overlap this on this particular coordinate system. We will draw a new one so that you can observe the difference here. This is x, this is y, this is 0, 0. So this is first unit, second, there is third, 4, 5, and there is 6. So here it is 1, 2, 3. Okay. So first point we will be getting it as 0, 0. So this will be the base. Next point will be 2, 0. This will be the second point. Third will be 4, 2. So this will be the third point. And fourth will be 6, 2. This will be the fourth point. So if you observe that there is a shear which has happened here. The component has changed its shape. The component has changed its shape. So initially it was a square. Now it has changed its shape. Here you can just observe this. There is a change in the x-axis. Y remains as it is. So the two parameter, that is the second y coordinate. So if you see, all the parameters are 2, 2 here, and the bases are 0, 0. The changes which is happening here is, this is the change which happens. Here it is 0, here it is 4, here it is 2, and here it is 6. So this is the shearing which will happen if you shear a particular parameter along x-axis. Similarly, it happens with respect to the y-axis. If you want to practice it, you can practice it with respect to y-axis. If I take this as shy is equal to 2, we'll be applying the y shear there. In that case, the component changes its y coordinate and x remains as it is. So I hope the shearing is clear here. Okay. So we'll go next with the reflection operation, how the reflection operation is to be carried out. So this will be the last operation in 2D transformation, that is reflection. You know the meaning of a reflection, and you have already performed this operation in your computer aided design, where in an AutoCAD or in a SolidWorks or any other modeling software, you have an option called as mirroring. Okay, you have an option called as mirroring. mirroring option, where an object will, if I want to have a symmetric reflection of an object on a particular axis with respect to a particular axis, I'll go with this reflection, what we call it as operations. For example, if I have a coordinate axis, okay, so I have a triangle here, I want to reflect this particular object. So whenever if you observe that whenever you are doing any reflection or a mirroring option, first you need to select the particular object. So which is the object you want to mirror, or which is the line, or which is the circle you want to mirror it, you need to select it. So in the options it will ask with respect to what axis you want to mirror. Okay, so whether it is a reference axis, whether it is a reference x-axis, a reference y-axis, or whether it is any arbitrary line. Okay, so whenever we are doing array options, so you can see the mirroring options with respect to a particular angle. Okay, so similarly you need to know the reference with which you are doing the mirroring. So for example, this is a component. If I want to mirror it with respect to x-axis, so what will be the mirroring option? With respect to the same distance, the object gets mirrored here like this. Okay, it is a reflection of this particular component. So this is the original component. When I mirror this component with respect to x-axis, you will be getting the component in this way. So if I want to mirror it in this particular y-axis, I will be getting the mirror in this particular fashion. So in the coming scenarios or coming concepts, you will be having such type of operations to be performed. So a component has to be mirrored with a particular axis or with a particular line. Okay, sometimes what happens, you need to mirror this with a particular arbitrary line. You need not to go with the axis. So how to do it? Okay, how to mirror it? What are the coordinates you will be getting? So whenever we are doing a theoretical, in your computer it is automatically being generated. So whenever we are trying to write it in a theoretical fashion, we need to know the coordinates. We need to know the matrix with which if I multiply my original coordinates, I should get the mirror coordinates. So mirrored coordinates, I should get it. So in that case, we'll be having basically 4 types of mirroring. Okay, 4 types of mirroring. First, we'll start with the basic axis. Okay, there are 2 axes here. As we are studying 2D transformation, there are 2 axes on which the mirroring operation has to be carried out. So first is, if I mirror or if I reflect the object with respect to x-axis, what will be the final coordinates? What will be the final coordinates? So for example, what is with respect to x-axis is, so if I have a component like this, I want to mirror this component with respect to x-axis. So x-axis will be the reference for me. This is x-axis and this is y-axis. X-axis will be the reference for me. I'll select this component. I'll select this as a reference. I want to mirror it. So when I want to mirror it, what will be the mirroring object? If you visualize it, it will come somewhat like this. Okay. So I need to know what are the coordinates of these points. So basically it has 3 points. So 1, 2, 3. That is A, B and C. So here you will be getting it as A dash, B dash and C dash. So these have certain coordinates with respect to an origin. So with respect to the origin, it is been located here originally. When I reflect it, these coordinates get changed. So you need to visualize how the change happens here. Okay. So if the logic here is, if I want to reflect it about x-axis, if you observe, the x coordinates remains as it is. So if you see the mirroring, the mirror has happened, there is a change in the y coordinates, but x coordinates remains as it is. The location of the x coordinates remains as it is, only there is a change in the y coordinates. So if you want to write what are the final coordinates of this, so what will be x dash? X dash is nothing but it will be equal to x. Okay, if you just observe this, a point has been shifted to a dash, but the line is same along the x axis. So you can see that x dash will be equal to x. What will be y dash? As it is a mirroring object, with respect to the base, how much is the distance? The same distance will be reflected back. As it is in a downward coordinate, okay, so if I go with the coordinate system plus y plus x minus x, so it is in the minus range, so we'll be writing it as y dash will be equal to minus y. Okay, y dash will be equal to minus y. So if I write the matrix for this, x dash y dash will be equal to, so how to write this? 1 0 0 minus 1 will be equal to x and y, will be equal to x and y. So just observe this, how we have done this. So we are doing the reflection with respect to x axis. When we are doing with respect to x axis, if you observe the figure, there is no change in the x coordinates. X is there, is in the positive way only there is a change in the y axis, and the y is in the negative form. So x dash will be equal to x, y dash will be equal to minus y. So x dash y dash 1 0 0 minus 1. If I want to write it in a matrix form, 1 0, 1 into x is x, 0 minus 1 into y is minus y. You will be getting same parameter. So you need to remember with respect to what axis we are doing the reflection operation. Okay, so coming to the next one, if I want to do with respect to y axis, with respect to y axis, which means that okay, this is the coordinate system. If I take this as a triangle here, I'll draw it a bit big. I want to take a triangle like this here, and this is x axis and this is y axis. Okay, so it has certain point. You can just observe that this is 1 point, this is 2, this is 3, this is A, this is B, and this is C. Take this point. If I want to do the reflection about y axis, about this point, if I want to do the reflection, I'll select the component, I'll select the reference point. So what will be the reflection? It will be somewhat like this. It will be somewhat like this, where if it is happening here, CAB. Okay, CAB. So what exactly is happening here in this particular case? If you observe, it is reverse of x-axis reflection. See here, when a reflection is taking place from this point to this point, y coordinate remains as it is and x changes to negative x-axis. It is shifted to a negative x-axis. If I want to write it as, in this case, x dash will be equal to minus x, y dash will be equal to y. Y dash will be equal to y. So if you just observe this, it is through this visualization only we can just understand what is exactly happening in a reflection. So it just reflected here. So when the reflection happens, x dash will be equal to x, minus x here, as it is shifting along x-axis. Y dash will be equal to y. Okay. So if I want to write it in a matrix form, x dash y dash. Okay. So what we will write? Minus 1 0 0 1. It will be x y. Okay, x y. Is it clear? So the next comes, I hope these two are clear, x-axis and y-axis. So next will be with respect to origin. If I want to reflect it with respect to an origin. So for example, if this is a component here, this is a component here, okay, so about this point I want to reflect it, about this point I want to reflect it somewhat, I want to get the component like this, okay. So with respect to this particular point, with respect to the origin 0 comma 0, if I want to reflect it, what exactly is happening here? So the component was in first quadrant, okay. When I try to reflect it to the, with respect to origin, it has shifted to the third quadrant. So what exactly is happening with the coordinates here? X and Y was in a positive zone. Now when I try to reflect it through the origin, it has gone to a negative zone where X is also negative, Y is also negative. In that case, how you will write it? X dash will be equal to minus X, Y dash will be equal to minus Y. So clear? When I want to shift it, reflect it with respect to origin, so you need to observe what will be the original coordinate, where in which coordinate system or in which quadrant it is initially located. Then when you shift it with respect to an origin, okay, so both will be in a negative axis, okay. So if I write it in a matrix form, X dash, Y dash, so what will be this? It will be minus 1, 0, 0, minus 1, X and Y. X and Y. Is it clear? I hope it is clear. When I want to reflect it through a origin, this will be the reflection matrix. Okay. So final one will come if I want to reflect it through a arbitrary line. Through a arbitrary line, what will be a reflection matrix? So if I want to write it in a arbitrary line, so for example, if I want to apply, okay, so we call it as X is equal to Y line here. This is called as X is equal to Y. Both orientation is same. If the component is somewhat here, I want to reflect it with respect to this particular object. Its coordinate system X dash Y dash will be equal to 0 1 1 0 X Y. So you need to remember this 0 1 1 0. So I have to reflect it with respect to this. There is a change in Y and as well as there is a change in X. As both are in a positive way, only the ordinate will change. How much will be the change in the ordinate will be this much. Okay. So you need to understand these all the four cases with respect to X, with respect to Y, and with respect to the origin, and also the finally with respect to an arbitrary point, arbitrary line. So this case is arbitrary line where X is equal to Y. Arbitrary line where X is equal to Y. I hope this is clear about the reflection. So regarding this problems on this, we'll be dealing whenever we are doing a sequential operations where number of different operations has to be performed on a particular component. In that case, we'll be dealing with this reflection examples. Okay, so we'll start with a new concept called as homogeneous coordinates. Okay, so today we'll be studying about the homogeneous coordinates. Why we need to write why we need these homogeneous coordinates? What is the use of this? How to use this homogeneous coordinates in the particular operations? Okay, so how it is best used? So we'll be discussing on those. See, till now we have studied different operations in the 2D transformation. If I summarize them, if I try to summarize them in the transformation, briefly if I want to summarize this, first we studied what is translation. What is translation? In that case, what we did is, if I want to take a point P dash, if I want to determine a point P dash, what we used to do? We used to write the translation matrix in this particular format. What does it mean? It is x dash y dash, okay, it is x dash y dash, where I need to know the value of the final coordinates. These are the translation matrix Tx, Ty plus our final, original coordinates. So this was the translation matrix. So if I try to write it the rotation matrix, if I try to write the rotation matrix, so P dash will be equal to r theta into P. What does this mean? This is a rotation matrix. So if you observe the two different matrices, one is having an additional matrix where we are to add the matrix. Here we have a multiplication matrix. In case of a rotation and scaling, we have a multiplicative matrix. So if you elaborate this particular case, you will be having x dash y dash, and the values are cos theta minus sin theta, cos theta into x, y. Okay. So if you see this rotation and scaling, we used to get P dash is equal to Sx or S into P, where you have Sx, Sy as the scaling factor, and you need to multiply with the particular point, original point, to get the final coordinates of that particular point. So if you observe this is a translation matrix or translation operation where we are doing an addition. We have to add the translation parameter to the original parameter to get the final coordinates. So here we are doing the multiplication factor. So multiplication factor, that is, you have to multiply these rotation matrix into the original coordinates to get the final coordinate values. So what is happening here is, there is a multiplicative factor and a additive factor. So in general, I can write the transformation matrix. In general, the transformation matrix can be written as, so P dash can be written in general as M1 into P plus M2. So what does this mean? In general, I can write this as M1 into P plus M2, where M1 is the multiplicative matrix, multiplicative matrix. You already know that P dash is the final coordinates. Okay, after doing the transformation, P is the original coordinates before doing any transformation matrix. So here this will be M2. M2 is the additive matrix. Additive matrix. Okay. So M1 is the multiplicative matrix, M2 is the additive matrix. So why we are writing this is, so when we are doing the operations, if you can observe this, translation is an additive matrix. Translation is an additive matrix. Rotation is a multiplicative matrix. Okay. So multiplicative matrix. So can I correlate this with respect to this particular case? So what happens here is, if I want to do only translation, okay, if I want to do only translation, you have only M2 value. M2 value. And what will be the value of M1? M1 in that case will be an identity matrix. 1 0 0 1. Okay, or sorry, it is an identity matrix, all the values will be unity. Okay, so what will be exactly m2 in the translation? You will be having tx ty. Okay, tx ty. So if it is an identity matrix here, whenever I am performing a translation operation, if this multiplicative factor is an identity matrix, anything multiplied to the coordinates, it will be same. It will be same, it will not change the value, so it will remain as p, and when you add them to the additive matrix, that is the translation parameter, so you will be getting the value for that particular operation. So for example, if the same formula, if I correlate with the rotation matrix or a scaling matrix, rotation is a multiplicative matrix. Okay, multiplicative matrix. So whatever the values are getting through the angle which we are getting, will be incorporating here, and later we'll be using the original matrix. What exactly will be the m2? M2 will be the 0 matrix here. 0 0 0 0 0 matrix here. Okay, so this is a general formula. This will be a general formula to solve the any transformation matrix. So here, what is the problem which we are facing here is, so sometimes you will be having a multiplicative matrix, some you will be having a additive matrix. So you need to do both the operations in the same particular case. So this becomes a bit a tedious case. In order to overcome this, so we will be using a term called as homogeneous coordinates. So this will be which we are using here. So if you use this, everything will be the multiplicative matrix. Everything will be the multiplicative matrix. So you need not to go with the additive matrix here. So what exactly is happening here? If I take a particular case where a square has to be translated to a certain point, for example, from the origin it has to be translated from a certain point, then from that point it has to be rotated by a 30-degree or 50-degree angle. In that case, what exactly is happening is there is a series of operations which are carried out. In such cases, if I go with the our basic 2D transformation operations, first you have to write the translation matrix, then multiply the original coordinates, then you have to form the final coordinates, then that coordinate has to be rotated. Okay, then that coordinate has to be rotated by an angle theta, whatever the theta angle is given. That rotation matrix you have to write it, then you have to solve it for the rotation matrix, and you have to write the final equation or the final coordinates of that particular case. In this homogeneous coordinates, what exactly we are doing is, we are trying to convert, if you see this particular matrix, this is a 2 by 2 matrix. If you observe this, this is a 2 by 2 matrix. In the homogeneous coordinates, which we are trying to convert a 2 by 2 matrix into a 3 by 3 matrix. Into a 3 by 3 matrix. So if I do that, I can directly combine the different operations in a single instant, and I can get the resultant matrix. If I get the resultant matrix, I can directly multiply with the coordinate system, and I'll be getting the values of the final coordinate. So this will be very useful whenever you are performing series of operations. So in this previous cases, what we have done is, we have just considered only one operation at that instant. Okay, a square has to be translated, a triangle has to be rotated, okay, a square has to be scaled. In that case, what we are doing is, we are performing a single operation at an instant. So when such cases comes, if you have seen, you have already done in a series of operations where it has to be rotated, where it has to be scaled at certain instant, how to do it in a single instant, we will be using this what we call it as homogeneous coordinate. So what exactly we are doing is, we are adding one more row and one more column here to make this particular 2 by 2 matrix into 3 by 3. So when we do this, all the matrix will be a a straight 3 by 3 matrix, so that multiplication of that matrix will be very easy. For example, if you see this translation matrix, it is a single column matrix, Tx, Ty. Okay, so multiplication, whenever I want to do the multiplication of that, it will be a tedious job. Okay, for that case, what we are doing is we are trying to convert them in a single format. So for that case, we are using a coordinate system called as homogeneous coordinate system. So basically we have a coordinate system x comma y. So now we are converting this x comma y into a 3 coordinate system, that is 3 by 3, by including a term called as h. X comma y comma h. X comma y comma h. H is nothing but a homogeneous coordinate. So h can be having any non-zero values. Any non-zero values. It can be 1, 2, 3, 4. Any non-zero values we can use it. But for the easiness of the solutions, always we will be taking h will be equal to 1. Always h will be equal to 1. So when I try to convert this 2 by 2, the original matrix, to a homogeneous matrix, this becomes xh, yh, comma h. So these are the values which we will be using it here. Okay, so always we will be using this 1 as a homogeneous parameter. Okay, so the same thing will be applying to the different operations and check what exactly the matrix will happen, okay, if I use a homogeneous coordinate to the different operations. So first we will go through that. I hope it is clear what is homogeneous coordinate. Exactly what I am just briefing it out. Whenever we are trying to use different operations in a single instance, you can see that translation is only a column matrix and rotation is a square matrix. So if I want to do individually the operations, it will take lot of time to perform the task. As we need to get the solution as early as possible, we will try to indulge this particular equation into a multiplicative factor. So if I multiply the matrix, I'll get the final resultant value. So in that case, this is not a simple column matrix. In that case, I'll be trying to make this as a square. So how to make this? This is a 2 by 2 matrix, this is a 1 by 1 matrix. So I'll be including a parameter h into the equation, where I'll convert this 2 by 2 matrix into 3 by 3, a common matrix. A common matrix, so which will be very easy to solve the particular problem. So for example, I'll write the translation matrix for this. So just observe whether there is any change in the particular case. So what I require is, I require x dash, y dash. I'll be using h as a dummy parameter. This is a dummy parameter here. So it is only used to balance the equation. This is x dash, y dash, h dash. So for translation, what we had, p dash is equal to t into t plus p. We had this particular format. So we'll be regaining the same format here. So if I write the matrix like this, 1, 0, tx, 0, 1, ty, 0, 0, 1, if I write it, and if I write it as x, y, I already told you this, what we call it as a homogeneous coordinate. For easiness of solutions, we will be using it as a 1. We'll be using it as a 1. Clear? 1. So if I do the multiplication of this, 1 into x is x, 0 into y is y, plus tx into 1 is tx. So what you will be getting? X dash is nothing but x plus tx. This is right. This is correct. Okay. So similarly, if I write y dash, 0 into x is 0, 1 into y is y, plus ty into 1 is ty. So as h is a dummy parameter, we need not to calculate it, or you can keep it as h is equal to 1. Already it will be there. H is equal to 1. So this is how we will be writing a homogeneous coordinates. So homogeneous coordinates for translation will be like this. So tx, ty, tz is there. I need to balance it. So x I have to get it. So I have to take on 1 as the element here. So 1 0 tx. So 1 into x is x, 0 into y is 0, tx into 1 is tx, y dash into for y dash 0 into x is 0, 1 into y is y, plus ty into 1 is ty. So you will be getting the same equation when you solve this particular 3 by 3 matrix. There is no change in the equation, but only the format has to be made so that whenever we are having a series of operations, we can perform it bit easy. Okay. So same thing I will be writing it for rotation. So same thing we will be writing it for rotation. So what we are doing in the basic one, p dash is equal to r theta. P dash is equal to r theta into p. P dash is equal to r theta into p. What we used to write it here? Basically x, y, here cos theta minus sin theta, cos theta into xy. This was the original one when we used to write. So now we need to convert this 2 by 2 into 3 by 3 matrix. How we will do it? Without altering the equation format, we have to do it. So I have already told you. So this is x dash y dash. So x dash y dash h will be equal to cos theta minus sin theta, cos theta, 0 0 0 0 1. So this will be the p by 3 matrix which we are getting for the rotation, the homogeneous matrix. So if I write it here, this will be x, this will be y, and this will be 1. Just observe, is there any change in the equation? So same thing, cos theta into x minus sin theta into y. So here cos theta into x minus sin theta into y, 0 into 1 is 0. Here sin theta into x plus cos theta into y, same thing is written here. Only we are changing the format of the equation so that it is equilibrium, and it is you will be understanding whenever we are doing a composite transformation where a series of operations has to be performed. So this is about the rotation. So if you want to go for scaling, scaling basically we used to write it as p dash is equal to s into p, where it is sx, sy. So how you used to write p dash, which will be x dash y dash, will be written as sx into 0 0 into sy x y. Okay. So now I have to write this particular case in a homogeneous coordinate system. So what we used to write? Parameters are x dash, y dash, h. H is a parameter which we are using, and when we use this sx 0 0 0 sy 0 0 0 1 into x y 1. Just observe what we are converted here. We have converted this 2 by 2 matrix into 3 by 3 homogeneous matrix. So everything is now equilibrium. So whenever I want to do the series of operations, I can just use these homogeneous equations to perform them, so that I will be getting the equations properly. Okay. So this is about the homogeneous coordinates. Homogeneous coordinates. So next we will be performing a composite transformation. So composite transformation. So what exactly is the composite transformation is? It is an extension of homogeneous application of homogeneous coordinates, where when a series of operations has to be performed. So for example, if you observe, whenever we have done the rotation operation, so for example, I'll tell you, if I am doing a rotation operation, how the rotation matrix was generated. We have taken the rotation from the origin. Just observe, initially the point was pxy here, and it was having an angle phi, and then you have taken a tilt, you have rotated anti-clockwise by an angle theta, So what exactly you are doing here is, you have rotated this particular line or a point through a origin. So through the point of rotation, a center point is origin. For example, if I want to rotate any point on a random distance, okay, this is a line is there. If you just observe, this is a line. I want to rotate it, this line, through this point. How exactly we can do it? Because we have generated the equation of whatever the rotation is there or whatever the scaling is there, we have done through origin. Scaling is also done through origin, and rotation is also done through origin. So if that has to be done, if the rotation has to be carried out from some random point, not through the origin, in that case you cannot use this directly. The equation. Okay, in that case what we need to do is, we'll be dealing that in the next class. This point, as we have generated the equation from the origin, the first point has to be brought to the origin, it has to be rotated, then it has to be sent back to the original point. So this is the logic we need to apply in the coming classes, so where a series of operations has to be performed. Okay, so in the next class we'll be dealing with the composite transformation. In that composite transformation, I'll be telling you how to rotate or how to scale a particular component or a particular object at any random point. Okay, so in that case a series of operations has to be carried out. So we will be using a series of homogeneous coordinates, then the application of homogeneous coordinates comes into picture there. So if I want to do individually, it will take a lot of time to do it. So if I can use the homogeneous coordinate in a single matrix or in a single multiplications, we will be getting the solution for that particular matrix. Okay, hope you understood this today's class, where we have dealt with the sharing operations, reflection operation, and homogeneous coordinates. So thank you.